people who are working in other fields to know exactly what is going on. And this is one of the reasons we are doing research, right? So to advance the human knowledge about the world around. And I think this is very important. I mean, I could.
Welcome to another episode of Traveling Through Space. And today I have Dr. Debarati Chatterjee, who is a researcher in theoretical physics, specializing in compact stars and gravitational wave science. Welcome to this episode.
Thank you very much for having me.
And you are presently the associate professor at the Inter-University Center for Astronomy and Astrophysics in Pune, and also a member of large number of international collaborations, including LIGO scientific collaboration. And since 2021, you have been a chair for education and public outreach for LIGO-India project. So this is all very fascinating and interesting. So I'm so excited to talk to you today. So again, welcome to this episode.
Thank you very much.
Awesome. There's a whole range of topics you can get into. But I was, hoping to start with, some of your motivation and influences. So cover some part of your journey. So I'm just curious to know, how did you get into what you're doing right now?
All right. So I come from Calcutta. So when I started doing my master's at the University of Calcutta, I was exploring different projects at different institutions and already like brainstorming what I can work on for my PhD. And I approached Professor Debarati Chatterjee, who was at that time working at the Saha Institute of Nuclear Physics. And so I was interested to do something in neutron stars. And this is because I had attended a workshop on the AstroSat project, which is already launched. So this is a multi-wavelength satellite launched by India. And so this workshop was conducted by the Tata Institute of Fundamental Research when I was a master's student. And I was absolutely fascinated by the idea of working on neutron stars because it's extremely intriguing and it's, very multidisciplinary. And so at that time, Professor Bandyopadhyay introduced me to the idea of gravitational waves, so neutron stars as gravitational wave sources. And this is something I found absolutely fascinating. So this is what I pursued my PhD on. So my PhD was in theoretical astrophysics and basically modeling the interior of neutron stars and how we can use gravitational waves as tools to probe dense matter in neutron stars. But at that time, gravitational waves, as you know, were not discovered. So I finished my PhD in 2010. And so there were already the LIGO detectors in place, but the sensitivity was not enough to detect directly gravitational waves. Although we know that gravitational waves exist because there were some indirect detections already before. So although it was a very fascinating field, at that time, the avenue, like in the future, was not clear. But luckily, in 2015 and 2017, there was the discovery of gravitational waves and from neutron stars. And this is when the community got really a boost. And also, luckily, this is also the time, around 2020, when I was looking for a faculty position. And when I joined IUCCA as associate professor, I immediately got into the LIGO scientific collaboration because there were several members there working in that field. And yeah, that's how I got into the whole thing.
Awesome. Yeah. And I, most of us following at that time clearly remember the 2015, 2016 time when the first detection happened, and it just seemed like, it became real for some reason. I think the scientific community knew it's real, but it just became more real for everybody else as well. I think for general public. So yeah, that was exciting times. Could you talk a little bit more about the Inter-University Center for Astronomy and Astrophysics? What is that about?
Yeah, so this is actually one of the premier research institutes in India, working in the field of astronomy and astrophysics. So it was the brainchild of Professor Jayant Vishnu Narlikar, who is like one of the very renowned professors in astrophysics in India and in the world. So the idea was to have an inter-university center in India, that can, let's say, boost the research scene in India by connecting and supporting the universities to come to the forefront of research. And so this has been already extremely successful. I would say IUCCA is a very small institute there, where like the capacity is to have about 30 researchers. I think currently we are about 20, and the community is growing. So we are connected to many different institutions across India and universities. And also we have worldwide collaboration. So basically this gives researchers associated with us a platform to come to the cutting edge of research. And yeah, also we have a sizable number of PhD students, although again, since we are a small number of faculty members, so we are pretty much to the best of our capacity, we try to support very good PhD students to introduce them into the world of research.
Nice.
And also right now, it's also the capacity of IUCCA is also growing, because we have several collaborative, let's say, like MOUs. We have an MOU with the Pune University as well, where we are training master students in astronomy. So there are also these kind of projects that are in place.
Right. Which makes a lot of sense, because it definitely seems like having access to information for research is quite vital to actually realizing what the actual subject is. So this makes a lot of sense, and you're sort of removing the bottlenecks of information spreading around. So this is awesome.
So kind of like to handhold the universities whose resources are often limited because of some of them may be very remotely located, or some of them may have very humble resources. But since most of the faculty members are already very experienced in research and also already part of many international collaborations, they can basically handhold these university teachers, professors into the field of research.
Yeah. No, that makes a lot of sense. All right. Switching gears a little, you mentioned compact stars with neutron stars and white dwarfs, and I mean, they're so far out of our daily experiences for most people on the Earth. So I'm just curious to know, how do you explain them to, let's say, a teenager?
Yeah, I was exactly doing that. So yesterday, the taxi chauffeur who brought me in Louisiana, he was also, so I just came here for the LIGO collaboration meeting, and he was also curious to know what's going on. So yeah, this is something I actually enjoy doing very much, because as you know, as researchers, we are very excited about the research we are doing, although it's very far from what people do in everyday life or understand, what is the importance of this. So yeah, I think it's, so the way I do it is to basically, maybe introduce the concept of what like stars normally do. So for example, the sun, which is our nearest star. So we know that it has we can observe the sun because it is burning fuel in its interior, but this is limited, and we expect that at one point this fuel, the fuel burning it is going to be run out. And then what we are doing is we are trying to explore the death of massive stars, which are even much more massive than the sun. And when these objects run out of fuel, they collapse. They basically, there's nothing to support them anymore against gravitational collapse. If you imagine, this is like almost like a balloon, and you pierce the balloon, and there's nothing more to support it. collapsing towards the center. And at one point, so there is a very massive core which is left behind called a neutron star. And the rest of the star is expelled into the interstellar medium in a beautiful supernova explosion. So some of these beautiful images of supernova remnants are you can see on the internet, on NASA pages and so on. So what is left behind this neutron star is an extremely intriguing object, because it is something like squishing the sun to a small radius of only about 10 kilometers. So you can imagine it's among the most massive and most dense objects in the universe. So if you like, it's like, laboratories in space which allow us to study matter, which is in such extreme conditions. Because as scientists on Earth, to explore fundamental matter, what we do is we build laboratories like nuclear and particle physics laboratories, or we build these giant, accelerators like the one at CERN. So, we smash particles in colliders to try and understand what is going on inside matter. But what is fascinating is that nature has given us these objects for free in nature.
Right.
And these are basically, laboratories floating in the cosmos. And so what we want to do is try and understand what's going on inside them. And one of the best ways to do it is by gravitational waves, because, we have right now a wide variety of telescopes which scan the sky across multiple wavelengths in radio and X-rays and gamma rays. But we are only limited to see things which emit light. Right? What about I think we all know now already that most of the universe does not emit light. So there is dark matter, and there are black holes, and there are neutron stars, much of which do not emit light. So we can only see a little bit of the universe that emits light with the help of these telescopes. So gravitational waves has basically opened up a universe in which if we can hear the sounds of something that we cannot see. So I think it's like a revolutionary field, and it's very, very exciting, because it's kind of like, opened up doors for us to explore the frontier of the universe that we could not do before.
Absolutely, absolutely. The multi-messenger astronomy has really taken off, so that's really great. And let me ask you about for a specific thing, specific topic, the space-time fabric. So, I think most people can make the jump towards understanding there is the concept of space-time, and how it's one thing to understand sort of keeping space and time separate. But what is space-time fabric? If you can, how do you explain that?
I think that, when we are children, we try to understand gravity from the eyes of what Newton first told us. So gravity, he understood it as with this falling apple, that there is something that's attracting this apple towards the center of the earth. So there is basically something that's pulling it towards the center of the earth. So it was a very nice and clear, explanation that works for most of the objects on Earth. So it worked pretty well to understand, okay, yes, if there are two massive bodies, they are attracting each other, and that is the force of gravity. But what happened is that as we progressed, we started to see phenomena which are not that simple, which do not hold with such a simple explanation. And now that, with the kind of precision we need to even drive our cars, and we need GPS to, a very high precision. So, this is already where Newton's gravity is reaching a limit. So now we venture into a more complicated concept of gravity. And so this was something that was introduced by Albert Einstein 100 years back in his theory of general relativity, which says that that space and time are not separate entities, but they are actually connected. So if you wish, I mean, what is space? Basically, when I want to describe the position of an object to you, I would say that, okay, if I tell you, let me ask you where you are sitting. So you are going to give me some coordinates. Like, okay, I am sitting here in the north of this and the south of this. But again, when you are moving ahead in time, you will not be sitting there, you will have moved, and there is something
Right.
else that would be there. So you are not describing your position accurately unless you also bring in time. So this is kind of like, the way of this describing the coordinate of any object in space. And so this space-time is something which is like a fabric, and all these cosmic bodies are embedded in this fabric.
Mm-hmm.
So usually we explain this by putting a stretch fabric or a sheet and putting like a heavy ball on it. So you can see that, these massive bodies, what they do is they curve the surface, and the more the massive object, the more the curve the surface is going to be. So it's basically, the idea is that, that gravity emerges out of the curvature of space-time around massive bodies. So this is, you can also easily understand, like if there is a curve, stretched space-time, a stretched curved fabric where you are having a massive body, if you throw a little marble towards it, it's going to fall towards that, potential, towards that
Right.
curvature, because, that is where it's, the most stable, that's its most stable trajectory. So this is very fascinating because it also says that even light, bends because of gravity. And this is something that, brought Albert Einstein to bringing such a picture, because these kind of phenomena were being discovered in, in astronomy. And to understand these kind of phenomena, like the bending of light because of curvature of gravity and so on. So these things introduce this concept. And so what is fascinating is that even 100 years later, now, even with all these, tests of GR, there are a lot of experiments being performed in astronomy to see whether Albert Einstein, he was wrong. And at some point, we will be able to, go to a frontier where, like Newton, we will prove Einstein wrong. But until now, there has not been any evidence. So
Right.
yeah, so this is, I think, a very fascinating concept. It's difficult to grasp, but it works wonders. So I think we are using this right now in GPS and in satellites and in the technology we are using every day. And this is an extremely successful theory.
Yeah, absolutely. And as you pointed out, through various experiments through the decades or the years, I think we have just kept proving Einstein right every time there have been more experiments. So that's fascinating. Um, and in your bio, we talked about how you work with analytical and computational models. Could you touch briefly on them as well?
Okay, so yeah, I mean, what is fascinating about neutron stars is the fact that, they are extremely simple objects, and they are also extremely complex objects at the same. It's difficult to imagine that, because when we say neutron stars, we can imagine by something like a ball of neutrons. It's a big ball of neutrons, which is not completely wrong. It's kind of like a giant nucleus floating in space. But also what's very complex is the fact that it spans a huge range of densities going all the way from the surface to the interior. So it's going from something like densities which we see in nuclear laboratories to something that is about 10 times of these kind of densities. And this is not seen anywhere in any terrestrial experiment. So even with the most powerful machines we have today, like, for example, these particle accelerators, which are these giant, heavy ion collision experiments where particles are smashed against each other, we can reach only about 2 to 3 times of that density. But inside the neutron star, which is only 10 kilometers radius, you can go 10 times of that density. So there is no experiment on Earth which can tell us what is going on inside. So what we do is we start off around the surface of the neutron star, which is something more or less we understand. But then as we go towards the interior, we see, a lot of fascinating physics that is, going beyond the current knowledge of physics that we have from laboratory experiments. So, for example, as it is going, as we are going, imagine we are sitting on the surface and we are walking towards the center of the neutron star. So first we are going to see some nuclei floating around a sea of electrons. And then as we go towards the interior, we start to see like very deformed nuclei. You can imagine something, it's funnily called pasta structures because they look like spaghetti and meatballs. So these are very squished nuclei actually. And they have funny shapes until at some point, because of the very high densities, even these nuclei are going to, melt into some kind of a fluid. And this fluid usually, mostly has neutrons, which is why it's called a neutron star. But very close towards the core of the star, you don't actually know what is going on, because from the knowledge of what we see in particle accelerators, we see a lot of exotic particles appearing at such densities. So these are called hyperons and quarks, and these are like extreme, they have extreme properties, and we only see them pop up like for fractions of a second. But in a neutron star, we think that these are going to be, stable components of its interior. So what is not clear is what these particles or what this kind of, strange phenomena are going to do to the structure of a neutron star, and also how it's going to influence the way it will emit gravitational waves. So this is something we try to infer. So what we do is we start off with the knowledge that we have from terrestrial experiments. Then we go on to, extrapolate these information to, with the help of some theoretical models. We think, okay, maybe nuclei start to behave like this, or nucleons start to behave like this when they come closer together and when, under these kind of extreme conditions. And then we see with our model, we try to predict what its structure is going to be like, or what its gravitational wave emission is going to be like. And then we compare with what we see from, for example, the telescope data or gravitational wave data, whether this matches what we are saying. If it doesn't, we go back to the drawing board and try to, put in more information or try, different models to see whether we are getting closer to what we actually see. So this is why we need analytical models, because we are running out of, the knowledge that we have from terrestrial experiments and going into a completely unknown regime.
Yeah, that makes sense. And I think one other example that comes to mind is how we resolved the image of the first black hole with the EHT experiment. And it was sort of, how can you clean that image up? And it was mostly done through analytical models and a lot of computational power behind it. So that's really great.
Second part of this conversation is coming soon. Stay tuned.